Today we're talking about parallelograms, and there may be a few properties you already recognize, but we're going to add to that and add a couple of details that might be new to you. So we're starting off just with a general observation here. We're not actually proving anything, but we're using a ruler to measure the lengths of sides and a protractor to measure the angles, just to look for patterns, right? I've pre-measured this already, but the concept is if we were to measure those sides, which ones would be the same, which ones would be different in length. So I have 5.4 centimeters for the left and the right side. They look to be the same. Yeah, sure enough they are. Top and bottom, 7.8 centimeters. So we have to be careful how we phrase this. We don't want to say they're all the same, because they're not all the same, but we do see that some are the same. So which ones are the same? Are they the adjacent sides? No, they're the opposite sides. So we would say not just opposite sides, but we would say both pairs, or two pairs of opposite sides are the same length. And if we were to measure the angles, here's my protractor. I'm measuring how many degrees we have in that angle, and we go all the way around. Again, we see some similar patterns. We see a 46-degree angle here at angle D, and on the opposite side, angle B is also 46 degrees. So those are opposite angles, and they are congruent. What about A and C? They look bigger than a right angle, and sure enough, they are. I measured that as 134. So again, we have to be careful. We can't just say the angles are all the same, because they're not all the same. We would see that the opposite angles are the same, but there's two sets of them. So we would say both pairs of opposite angles are congruent. We can go a step farther and take a look at the consecutive angles. Now these are not adjacent angles, so we have to be careful here. Remember, we said that, or we've learned that adjacent angles have to share the same side and the same vertex. These two angles do share the same side, but they don't share the same vertex. They have two different vertices. So they're not considered adjacent, we call them consecutive. Consecutive angles add up to 180 degrees. These are also consecutive angles. They share the top side. They add up to 180 degrees. These are consecutive angles. They share the left-hand side. They add up to 180. And these are consecutive angles. They also add up to 180. They share the right-hand side. So that's an observation that we can make as well. Opposite sides are congruent, both pairs of them, and consecutive angles are supplementary. Now let's go a step farther here, and let's draw the diagonals. You can make a general observation if they look to be the same length or not. No, they are not the same length. Clearly one is longer than the other. This long one, I've measured that to be 12.4. Now we're going a step farther here, and we're saying, okay, if we were to consider a point here where the two diagonals cross, what do we know about the length from the left side to that point and the right side of that diagonal to that same point? What do we notice about those? Those happen to be the same length. 6.2 centimeters are the same. So in other words, we have a midpoint right here. The other diagonal bisected the larger diagonal. So we have two congruent segments. So the question is this shorter diagonal also bisected? What are its lengths? So altogether, I have 5.6 centimeters in length. And when we measure each half, they are the same. They are 2.8 on each side. So once again, yes, this is midpoint for both diagonals. The short diagonal is bisected and the long diagonal is also bisected. So we're going to summarize all of those properties in the box below. These are the properties of a parallelogram. And notice the phrasing here. All right, we start off by saying both pairs. So we can indicate exactly how many times we're seeing this pattern. Both pairs of opposite sides are parallel. Well, that kind of makes sense. It is a parallelogram after all. This is the actual definition of a parallelogram. So that's not something that we measured in the diagram above, but that kind of describes the shape that we're working with. Of course, both pairs of opposite sides are parallel. When we did measure it, we saw that both pairs of opposite sides are congruent. When we measured those angles, we saw both pairs of opposite angles are congruent. And when we looked at those consecutive angles, we saw that those consecutive angles are supplementary. And in case you forget if that's the 90 degree or the 180 degree, let's jot down that's the 180 degree, right? They add up to 180 degrees. Lastly, we looked at the diagonals, and we saw that each diagonal was bisecting the other. So we say the diagonals bisect each other. Those are the 5 properties, and you need to know those, you need to memorize them. We're going to be looking at some examples here in a moment, using these properties to set up equations and solve for variables, but these 5 are the ones that you also need to know, like how to say it correctly. So don't just say opposite sides are parallel, say both pairs of opposite sides are parallel. Use this kind of wording that you see right here. All right, let me turn the page over. Let's take a look at a couple of these. Now I know it says here at the top, let's prove some of these properties using a rotation. So this is not a formal proof, it's actually more of a demonstration. But you might remember when we were doing translations and rotations and other kinds of transformations in general, we would find that if we were to move an object, like if we were to translate it, it would stay the same size and shape. We call that a rigid translation. Or we could take this and reflect it. And if we were to reflect it someplace else, it was the same size and shape. We call that a rigid reflection. Well, here, let's do a rotation. And we're going to rotate it right about the midpoint. So again, if we drew another diagonal here, that would be the midpoint. So we're going to rotate this triangle. And guess what? It's the same size and shape. It maps onto itself like this. So what that means is the top length, which we found here, must in fact be the same size as the bottom length. So that's how we can see that, yeah, we do have opposite sides that are congruent. Of course, this is true with the right side and the left side. We rotate the triangle around. Because the triangles are congruent, those corresponding parts must be congruent as well. And there you have it. And we could go on, we could look at the angles, right? Here's angle D. We could rotate that around the midpoint, and sure enough, it's congruent to angle B. So many of those properties we saw earlier, you can also show with a rotation of triangles. Here's example number 1. We have a parallelogram. Notice the arrows here, the left and the right side have a single pair of arrows. The top and the bottom also have a double set of arrows. That's how we know both pairs of opposite sides are parallel. That's how we know it's a parallelogram. We have a few variables here. We have an x on the bottom. We have a y on the inside. We have a z on the inside. We have to find each of those. So let's start off by finding x. When you take a look at this information, part of the challenge is just reading the diagram correctly and knowing what part of the figure it's describing. The 2x minus 3. You can see it's kind of stuck here on the bottom edge. Just notice there is no degree symbol. It is not an angle. If it's not an angle, it must be the side length, right? It's describing the length all the way from k to n. That's the length of kn. In the same way, the 37 at the top, there's no degree symbol there. That's not an angle. It's the length of the side, and that goes all the way from L to M, right? We said opposite sides are going to be congruent, and that's the same here as well. If they are congruent, that means they are equal in their lengths. So we set the top and the bottom equal to each other, and then we'll solve for x. Add 3 to both sides, and then divide away the 2. X is 20. Here is the variable y that we're solving for. We said opposite angles are congruent, so we set those equal to each other. And in this case, the variable y is already by itself, so there's no more algebra to do. We found it. Next, let's find z. Again, we said the opposite angles are congruent, but there's no number at angle m, so I can't just say z equals this number because there is no number. So we need a different pair of angles to look at. So instead, let's take a look at the left-hand side. Remember, we said if two angles share a same side, those are consecutive angles, and we know that the consecutive angles are supplementary. They should add up to 180 degrees. So that's how we'll set up our equation. The 123 plus the variable z sum up to 180 degrees. Subtract the 123 from both sides to get your variable by itself. 57 is the answer. Let's talk about those angles again in example 2 as we talk about a few angles, 2 angles here in this parallelogram. We'll draw our diagram so we can label our information here. Here's my parallelogram. And in the information, they're describing these 2 angles in this way. They say one angle of a parallelogram is 20 degrees more than another angle. And we have to find both of them. Here it says using algebra, meaning don't just guess and check, let's set up an equation and solve it. So we're talking about 2 angles, the one angle and the another angle. Are they the same size? No. One is bigger. It's 20 degrees bigger. If we were talking about these 2 angles, those would be the same size, right? Opposite angles are the same size. But because we're talking about 2 angles that are different sizes, we're not talking about 2 angles that are opposite each other. We must be talking about 2 angles that are consecutive to each other. So I have a smaller angle and a bigger angle. So this is my smaller angle, the another angle, and the one that is the 20 degrees more, that's the larger angle. So we need to pick a pair of angles, one small and one big, and I'll use these 2 on the bottom. The small angle's on the left, the bigger angle's on the right. Okay, so we know that this bigger angle is bigger by 20 degrees more. We're going to add 20 degrees onto the smaller angle to get that bigger angle. So how much is that smaller angle? We don't know. They didn't tell us how many degrees. So this is the one where you pick a variable. Right? So if I pick the variable a, for example, that will go here in my diagram, and that's a degrees. So then the larger angle is 20 degrees more than that. So this is the a plus 20. So that goes up here in the larger angle, a plus 20 degrees. And because those are consecutive angles, they are supplementary, so we can take those 2 and add them up to 180 degrees. So we'll combine like terms. A plus a is 2a. Subtract the 20 from both sides, and divide away the 2. So let's take that 80 and plug it back in. So we can see that this angle on the bottom left is 80 degrees, and this angle here on the bottom right is 20 degrees bigger than that. So 80 plus 20 is 100. Sure enough, they add up to 180. Here in example 3, we're looking at a few more properties involving the diagonals. Take again a close look at the information that you see. Take a closer look at 12. I want to use that one as an illustration here. Sometimes I have students who have trouble figuring out what that 12 belongs to. Like, does it belong to this top side? Does it belong to this diagonal? Does it belong to this angle here? Does it belong to this angle? Which part of the figure is it describing? Same with this 27. Is it belonging to this angle, to this diagonal, to this side? Right, if the figure is small and there's lots of information in there, it can be hard to figure out exactly what we're looking at. So again, use the degree symbol to help you identify if it's an angle or not. If you look at the 12, is there a degree symbol? No, there isn't. So we know it's not an angle. It must be a side length or a diagonal length. Which one is it? Typically, we'll put the side lengths on the outside, like what you see here in example 1, and we'll put the diagonal lengths on the inside of the figure. So this 12 is describing the length of the diagonal from the vertex to the midpoint. You also see the 3x plus 6. Now that's on the outside, but the arrow is bringing us inwards, so that's describing this diagonal length here. We learned there's a midpoint, so we have two congruent segments. So to find x, we will set the two segments equal to each other because the midpoint creates two congruent segments. So the 12 is equal in length to the 3x plus 6. Let's solve for x. I'm going to subtract 6 from both sides and then divide away the 3 to find the variable y. We have a very similar process. The 2y plus 9 is describing the length of this diagonal on the left-hand side. So because of the midpoint, we see that there are two congruent segments. We'll use the 2y plus 9 and the 27 to create our equation. 2y plus 9 equals 27. Subtract 9 from both sides, and then divide away the 2. And we get y is 9. So let me use this final picture here just to point out a particular feature. We're not going to go through all of these questions here. I just want to highlight a couple of details. Remember, this is a parallelogram. And when we have lots of pieces of information on the inside, mainly with those angles, I want to show you a pattern. I want to show you something to look for here. Let's focus on the top and bottom sides. So I'm going to extend them a little bit. And I'm going to use one of those diagonals as a transversal, right? The transversal cuts across two parallel lines. We've studied this pattern before, right? In a very general sense, if you have parallel lines cut by a transversal, we've learned that the parallel lines form angle pairs that are congruent. Specifically, we can take a look at this angle and recognize those are alternate interior angles. They have to be congruent if they're touching those parallel lines. We see that showing up here as well. Because we have a parallelogram, we know the top side will be parallel with the bottom side, so treat those like your parallel lines. Treat the diagonal like your transversal. So this information that you see here, the 28-degree angle, can you find its pair? Can you find the other angle that will also be 28 degrees? Right up here. We know that because those are alternate interior angles. In the same way, you have a 23-degree angle here. So it's touching the parallel line at the top, so we can use this diagonal as a transversal, which means we would find its pair down here. So this is also 23 degrees. Right? So you can see how we're using those alternate interior angles to fill in a bit more of the diagram. Now let's go one step farther. See that we have 4 triangles? I'm going to zoom into that top triangle. Let's take a close look. Notice I have 2 of the 3 angles, 23, 28, and this angle right here. We could find that angle, I think one of these questions in fact wants us to, but we can find that because the 3 angles in a triangle add up to 180 degrees, right? So we could keep on going. We could find this angle, we could find this angle, we could find more, but I just wanted to highlight that particular pair of those alternate interior angles. And we'll wrap this up right here.